This is the first of 3 lectures from chapter 14, which is all about equilibrium. And I think there are actually 3 chapters on equilibrium, so it's quite an extensive topic. The first thing that you need to get under your belt is an understanding of what equilibrium is. The first requirement for equilibrium is that a reaction is reversible. And so notice that in this made-up reaction, C and D are the products. If we talk about the reverse reaction, what we mean is that the products of the initial reaction, that is C and D, are now reactants, and they are reforming the original reactants A and B. So that is the reverse reaction. So for a reaction to reach equilibrium, the first requirement is that it must be reversible, and not all chemical reactions are. So if you imagine burning a piece of paper, no matter how hard you try, you're not going to be able to pick up those ashes and get your original piece of paper back. So not all reactions are reversible. What is equilibrium? Equilibrium, and this is a really commonly misunderstood concept, is the point in a reaction, in a reversible reaction, at which the rates are equal. So at equilibrium, the rate of the forward reaction, the rate at which product is formed, equals the rate of the reverse reaction. Okay, the rate at which product or reactant is reformed. There are 2 graphical representations of equilibrium that you should be able to interpret and that may help you understand it. The first is a graph of concentration versus time. So let's look first at the reactant concentrations. Obviously, in the beginning of the reaction, when you have only reactants, their concentration is the highest. And you would expect over time the concentration of the reactants to decrease. Likewise, in the beginning of the reaction, the concentration of products is 0. But over time, as the forward reaction progresses, you would expect the concentration of the products to increase. So what's going on when we have these plateau areas? Well, clearly at the plateau area, there is no more change in the concentration of reactants and products. That is equilibrium. All right? So notice that the concentration of reactant and products are not the same, okay? And that's probably the most common misconception of students. They think that equilibrium means concentration of reactants and products is the same. It absolutely is not. That's very important to know. The concentration of reactants and products are different at equilibrium. They may coincidentally be the same, but in general they're different. However, they cease to change. The concentration stopped changing. Okay. Now let's look, instead of plotting concentration on the y-axis, let's put the rate of reaction on the y-axis. Let's look at the rate of the forward reaction first. The rate of the forward reaction is at its highest at the beginning when the concentration of reactants are highest. The rate is going to decrease as the reactants get used up and there are fewer collisions. Conversely, the rate of the reverse reaction starts at 0 because there aren't any products to go in reverse in the beginning. The rate of the reverse reaction picks up with time because as you build up more product, the products undergo more collisions with each other and can reform reactants. At some point, and this is important, the rate of the forward reaction equals the rate of the reverse reaction. And that is equilibrium. Okay? So concentrations don't equal each other, they just stop changing, but the rates actually coincide, they equal one another. All right, this is just a larger view of what I just went over. I'm not quite sure why I felt compelled to put it in again, but I'm going to move on. All right, so the conventions, how do chemists demonstrate that you have a reversible reaction that is capable of reaching equilibrium? They use the 2 arrows. This is not the same as a double-headed arrow, by the way, which is used for something we call resonance structures. But the 2 arrows, one going forward, one going reverse is what you'll see for reversible reactions. All right, and this little ant animation you can ignore in PowerPoint form. It's just a visual that shows equilibrium. So the little ants are moving back and forth at the same rate, but the quantity of reactant and product is different. So you can see that I find a number of ways to try to get the message across that equilibrium does not mean equal concentrations of reactants and products. So it's also important to understand that equilibrium is dynamic. What do we mean by that? Well, just because the concentration of reactants and products stop changing at equilibrium does not mean that there is no activity going on. As a matter of fact, the forward and reverse reaction are both proceeding regularly during equilibrium. But since they're proceeding at the same rate, you cannot see any difference. So imagine if you had people, this is countries, but you can imagine, I always say classrooms, and I start telling you to move back and forth from one classroom to the other. If the people move back and forth at the same rate, in other words, if 3 people move from country A to country B in the same amount of time that 3 people move from country B to country A, although you were going to have constant movement, you are not going to have any net change in the population of the 2 rooms. That's another analogy for equilibrium. There's a mathematical expression called the equilibrium constant expression, represented by a capital K. Now it's important to notice that it's capital K. Lowercase k is the rate constant. And so the equilibrium constant is an expression, which I'm going to explain to you in a moment, that gives a chemist an idea of the position of the equilibrium, how much reactant and how much product are both present at equilibrium. That relationship between product and reactant as expressed by the equilibrium constant is called the law of mass action. That's just a vocab term. And so here's the generic form for the equilibrium expression K. There are all sorts of little equilibrium reactions, acid-base reactions, solubility reactions or interactions. So you'll notice this little subscript for the equilibrium constant changing, but don't get concerned about that now. But the basic expression for an equilibrium constant expression, if you look at this reversible reaction, take a look at the equilibrium expression. What is in the numerator? It is the products. Products are C and D, but also notice there are exponents, okay? Oh, and this exponent should be D, okay. When writing an equilibrium expression, you look at the balanced equation, and whatever coefficient is in front of a substance becomes the exponent in the equilibrium expression. In the denominator, then, are the reactants. So, in short, we think of the equilibrium expression as products, concentration of products over concentration of reactants. So, as you can imagine, K, the equilibrium constant, gives us an idea of how much product is formed. The larger it is, it means the more product there is. And be extra cautious here because the rate constant, lowercase k, where when we use that and we wrote an expression for the rate law, so if we say rate law equals K concentration of the reactants, remember that in kinetics, we're not allowed to put the coefficients in front of reactants as exponents. These exponents in kinetics have to be determined experimentally. So make a note to yourself not to confuse those. Let's look at a real example. If we have dinitrogen pentoxide, it decomposes into nitrogen dioxide and molecular oxygen. The equilibrium constant expression, just to see a real one, remember it's products over reactants. And so we have concentration of nitrogen dioxide raised to the power of 4, and that comes from the coefficient, times concentration of oxygen gas divided by the reactants, okay, which is dinitrogen pentoxide, squared because of the coefficient. Simple. Here are a couple more examples. No surprises. However, I want you to focus on the example at the bottom of the page. We have a reaction here. That's decomposition of calcium carbonate, which is chalk. And look at its equilibrium expression. You'll see a lot of K sub C. That just means equilibrium constant in terms of concentration. What's going on here? All we have is carbon dioxide in our equilibrium expression. What happened to calcium oxide and calcium carbonate? What do you see in common about those two? Hopefully you notice they're both solids. As it turns out, solids, pure solids, so not solids that are dissolved in water, but pure solids and liquids are not included in the equilibrium constant K. And that is because pure solids and pure liquids, not ones that are dissolved in something else, but pure solids and pure liquids have a set concentration that doesn't change. And so they're just, since it's a constant, they're lumped in with a value for K. They are not put over in the right side of the equation, which implies they can have variable values. So for example, water, its molarity, and I hope I don't get this wrong, it's something like 55.6 moles per liter of H2O is the concentration of water. And it's not going to change. It's a constant. So water, pure water, is never included in an equilibrium expression. Let's talk about values of K. So remember that K, just real generically speaking, is products over reactants. We know it's not that quite that simple. But in general, as K becomes large, what does that mean? That means you have a lot of products, okay? And as K becomes small, that means that you have a lot of reactants, okay? If you have a lot of reactants, that means your denominator is large, which makes K small. So those are important concepts to understand. So putting into more mathematical terms, let me pull this page up a bit here. If K is larger than 1, okay, that means that products are favored. Okay, that means that the numerator is larger than the denominator. So if K is larger than 1, products are favored. That would be a good thing for chemists. So when they're industrial chemists, when they're looking to do a reaction and they want to make sure they get a good amount of product so that it's cost efficient, they look for a reaction with a large K. Conversely, if K is much less than 1, that means the denominator is very large. That means that reactants are favored. You're not going to get very much product if K is less than 1. Okay, so it's called a reactant-favored equilibrium. The final concept I'm going to review in this first video is how the values of K can change for the same reaction. And it all depends how you express your balanced chemical equation. So let's just look at the generic chemical equation, A plus B equals C and D, and the regular equilibrium constant expression is right here. However, what if somebody, instead of writing the equation in this form, just flipped it and wrote it as the products beginning as the reactants, which is perfectly fine. Would it have the same equilibrium expression? No, okay? Because in this case, what was the reactants originally, A and B, are now products. So in this case, A and B would be on top and C and D would be on the bottom. Just as if you flipped the original equilibrium expression upside down. So an expression, I wanted you to understand where it came from, but the bottom line is the equilibrium constant for a reverse reaction is 1 over the equilibrium constant for a forward reaction. So if K for a forward reaction was, let's just say 500, arbitrary, okay, that means that K for the reverse or backward reaction would be 1 over 500, right? So that's one relationship you need. Here's another way to change the value of the equilibrium constant. Let's say, again, let's look at initial generic reaction. And let's imagine that for whatever reason we have that same reaction, but we've multiplied all the coefficients by some factor. In this case, 2. Would it have the same K? Well, no, it would be different, because now, whereas let's imagine that each coefficient in the left-hand standard equation was 1. Okay, so that means the K we wrote would just be concentration of C divided by concentration of A times concentration of B. Now we've doubled, so now instead of all of the exponents being 1, they're all 2. So the value for equilibrium constant would be quite different if the coefficients in the same reaction are different. So what is the general mathematical equation between that? Well, whatever factor you multiply a chemical equation by, in this case 2, becomes an exponent for the equilibrium constant value. In other words, the new K equals the original K raised to whatever the factor that you multiplied the equation by. That becomes an exponent. So let's work a couple problems. So what I recommend at this point is that you put the video, the lecture, on pause, and you see if you can do these yourself. There's one of each, one where you reverse the reaction, and another where you multiply it by a certain factor. So give it a try on your own first, and then I've got the answers on the next page. Let's look at A first. The original reaction starts with dinitrogen tetroxide. It gives you the K value. Now, what have we done with this chemical equation? We've simply flipped it. It's simply the reverse of the original one. And so what was the expression I said you need to know? When you reverse a reaction, the new K, so we'll call it K of reverse, equals 1 over the original K, and we'll call that K of forward. So the new K is 1 over 4.63 times 10 to the minus 3. If you carry that out, that means the K for this reverse reaction is 2.16 times 10 squared, or 216. K is unitless. I don't know if I have mentioned that, but we don't use units. They'd be constantly changing, so K is treated as a unitless value. All right, part B, a little bit trickier. Analyze the reaction, see what we've done. First of all, we've reversed it, but we've also multiplied it by what? Well, now instead of a 1 in front of dinitrogen tetroxide, there's a 1/2. Instead of a 2 in front of nitrogen, I don't know, I think I said those wrong, there's a 1. So we basically divided by 2, or I'm just going to say multiply by 1/2. That's easier for me to get my head around. So we need to do two things to the K value. First, we need to put 1 over the original K, but then we also need to take that original K and raise it to our multiplication factor, which is 1/2. So your answer is, let's plug in the value. The original K is 4.63 times 10 to the minus 3. Boy, I'm getting sloppy here. Okay, raised to the 1/2 power. And of course, anything raised to the 1/2 power means square root, right? And so go ahead and plug that into your calculator and make sure that you're doing the order of operations correctly and that you get the K value of 14.7. and I fibbed a little. I told you manipulating K was the last concept, and I forgot that I want to talk to you a little bit dealing with gases. If you have a reaction in a gas phase, and of course gases exert a pressure, and what you may not remember is that the pressure is directly proportional to concentration. Okay, so as concentration goes up, pressure goes up. Remember that pressure is due to collisions between gas particles and container walls, and so obviously the more gas particles you have, the more collisions and the more pressure. So you will often see, if there are gases involved in a reaction, an equilibrium constant is called Kp, which means it's expressed in terms of pressure rather than concentration. Kp and Kc are typically different. They can be the same under certain circumstances, which I'll show you, but don't make that assumption. Usually they're different. And so you can see it's quite simple. Instead of expressing concentrations of each of the products and reactants, we express it in terms of the pressure. Obviously, only gases have pressure, so if you have a Kp, no solids, no liquids, okay? They don't exert enough pressure to be included. Everything else is the same. You still have the exponents that used to be the coefficients in the balanced equation. So the mathematical expression for Kp, equilibrium constant in terms of pressure, is right here. So it equals Kc, the equilibrium constant in terms of concentration, multiplied by R is always the gas constant. Doesn't that just seem to show up everywhere? Okay. Times temperature in Kelvin. Okay. And delta N. What is delta N? Delta N is the difference, that little triangle means difference, between the moles of product that are gas minus the moles of reactant that are gas. In other words, it's the difference in the moles of or molecules of gas comparing the reactant to the product. Boy, I feel like I butchered that. That'll be more clear when we do an example. But I want you to look at this mathematical equation and just see, when would Kp and Kc equal each other? They would equal each other if this whole term, RT raised to the delta N, equals 1. When would that equal 1? Well, when the exponent delta N equals 0, because remember, anything raised to the 0 power is 1. So let's look at some examples when the difference in the number of gas molecules equals 0 and doesn't equal 0. Let's see what we have. Here's a straightforward example which I'll work for you. If equilibrium constant in terms of concentrations, 5 times 10 to the 6, equilibrium problems will always tend to throw in temperatures. Don't really let that throw you off. It's usually just a distractor. You may remember from previous lecture that the only time the value of an equilibrium constant will change is if temperature changes, so it's typical for scientists to include a temperature. Anyway, so let's look at the reaction. It turns out that all the reactants in the products are gases. Okay, so the equilibrium constant could be expressed in terms of Kc or Kp. So let's go ahead and write out Kp to begin with, and then I'll plug in values for you. So if you were to write out the expression for Kp, instead of the brackets for concentration, you just put a big P. And then the substance itself gets written as a subscript. So pressure of SO3, and that would have to be squared. Okay, that's the only product. And then in the denominator, whoop, I'm ready to mess it up already. Pressure of SO2 squared times pressure of O2. Okay, that's it. That would be the Kp expression. But you don't even need to write that to solve this problem, because you have the equation I just gave you relating Kc and Kp. So let's see what that looks like. All right, so here it is. Let's just plug in our values. The problem gave us the value for Kc, so we're going to plug that in. You always have to use an R value that matches units, and the 0.0821 is liters, atmosphere, mole, Kelvin. And since we are using Kelvin, you want to make sure you use this value of R. And delta N is what I really want you to focus on. Delta N is the difference in the number of moles of gas on the product side minus the moles of gas on the reactant side. How many moles or molecules of gas do we have on the product side? Exactly 2. Okay. How many moles of gas or molecules of gas do we have on the reactant side? We have 2 plus 1, or 3. So delta N equals minus 1. So that's what ends up as the exponent. When you plug all these values in, you get that Kp, which is the equilibrium constant in terms of expressions of gas pressure, is 8.7 times 10 to the 4. Okay, that is different than Kc. They're both large values, which is appropriate because that means this is a product-favored reaction. Okay, remember, if you have a large K value, it means that products are favored. You've built up quite a bit of product, so it would be a good economic reaction to carry out. Now we really are getting close to the finish line, the fishing line. Okay, so you go ahead and try this one on your own. Calculate Kp, gave you Kc, similar to how I did it. They're all gases, so no confusing factors. So shut off the video, give it a try, and then compare your answer in the next slide. And here it is. Again, how many, the key here is getting delta N correct. So you have 2 gas molecules on the product side. 1 plus 1 is 2. How many do you have on the reactant side? 1. That means delta N is 1. Okay? And so Kp is 229. I do want to show you something that's important when writing out equilibrium expressions in terms of gases. Let's go back to the decomposition of calcium carbonate, chalk. That can break down to calcium oxide, okay, those are solids, and carbon dioxide, which clearly is a gas. If I were to ask you to write the equilibrium concentration in terms, the equilibrium constant in terms of concentration, remember that solids and liquids are left out. So you would simply write concentration of CO2. It's the only one that's not a solid or liquid. And by the way, if you have a solid dissolved in water, let's say sodium chloride dissolved in water, and that's designated with an AQ, aqueous symbol, that gets included in your equilibrium expression. So it's only the pure solids that get left out. So the Kc expression for this reaction would simply be concentration of CO2. What would the Kp expression look like? Remember that in Kp you only include gases. So the Kp expression would be pressure of CO2. That's it, okay? So you just have to be aware of the limitations on these. So to sum up the exceptions, concentrations of pure solids and pure liquids are not included in the equilibrium expression because their concentrations don't change. And so let's write this example, and I wanted to show you this because it has an aqueous term, and I want you to know that aqueous terms do in fact get included in the equilibrium expression. So you'll notice when we write the expression for K, both products are included. Water is not. Okay, again, water's a pure liquid. Its concentration is not going to change, so it's just lumped in with the K value and is not shown in the equilibrium constant expression. Here's a visual showing the same concept. I know that even still sometimes it's hard for me to believe that the amount of solid or liquid you add to a reaction is not going to change the rate. So this visual might help. So here's a reaction where we're showing carbon monoxide being converted to carbon dioxide and solid carbon. If you were to write the equilibrium expression K, this is what it would look like, and the solid carbon, which is shown here, would be left out of the expression. Just to show you, comparing these two bell jar samples, on the right there's obviously a whole lot more of solid carbon, which is basically like your charcoal briquettes that you grill with on a Weber grill. But it's showing you that even you can dump in a whole lot more solid carbon and it's not going to affect how much carbon dioxide and carbon monoxide you have. It's not going to shift the equilibrium toward product or reactant or anything. So it's not going to have any effect at all. So what that simply means is, although the reaction needs solid carbon to proceed, it is not affecting the relative rates of the forward and reverse reaction. And that is the end of the first lecture for Equilibrium, Chapter 14.